So I think we can start. It's 2 p.m. here in it's 2 p.m. here in Central Europe, and I will follow the sun. So I will start saying good evening to the people from Japan, and China, and in general Asia. Good afternoon to the people who are here from Europe, and good morning to the people who are here from US. This is the 5th seminar of the fall season of the IJMF Spotlight Seminar Series, and I see a very good audience. I remind you that our last seminar of this season will be in 2 weeks from now, and it will be given from US, so time will change a little bit and we'll receive due notice. I thank you for participating to this series, and I just now leave the word to Professor Chao Sun, who will introduce the speaker of today.
Okay, thank you, Alfredo. Thank you, the editor-in-chief of our journal. So, my name is Chao Sun. It's my great pleasure to chair this talk. So today's speaker is Professor Bin Ji. Professor Bin Ji joined Wuhan University as an associate professor in 2015. And he was appointed as a full professor in 2018. Before he joined Wuhan University, he received his PhD from the Department of Thermal Engineering from Tsinghua University in 2011. And he also worked as a postdoc researcher at Tsinghua University for several years. His main research interests about the fundamental aspects of the cavitating flow. Dr. Ji received a Peiyuanzhou Award in 2018 in hydrodynamics and the NSF Award for Excellent Young Scholar in 2018. So, Professor Ji, floor is yours. Okay, could you try and share screen? You first unmute yourself, then you share screen. So, Professor Ji,
can you see my screen?
Yes.
Okay, Chairman, thank you very much for your introduction. Good morning, good afternoon, and good evening for everyone. First of all, I would like to thank everybody to join this IJMF Spotlight Seminar. I'm Bin Ji from Wuhan University in China. It's really my pleasure to be invited to give a speech about our recent investigation progress. My topic today is mainly about the characteristics of tip-leakage vortex cavitation and its control. This is the outline of my presentation today. It is well known that in actual hydraulic machineries, the gap between the blade tip and the casing is generally indispensable. Okay, I show due to the pressure difference between the pressure side and the suction side, part of fluids near the tip may pass through the gap and move from the pressure side to the suction side. And the flow is called the tip leakage flow. It will induce complex vortex structure near the gap. The pressure in the core of a vortex generally is quite low. And if pressure is low enough, cavitation will happen, just as shown in these videos. It is called a tip-leakage cavitating flow. Sometimes we also call it a tip-leakage vortex cavitation, here abbreviated as TLV cavitation. Once TLV cavitation happens, it will significantly affect the local flow structure, which will not only lead to the decline of the performance of hydraulic machineries, but also significantly enhance vibration, noise, and cavitation erosion. In the past decades, many researchers have carried out a lot of research work, such as TLV in rotating machinery and a cascade single blade. This investigation indicates that the TLV cavitation induced by a single blade can reflect the main characteristic of leakage flow inside rotating machinery, and the law obtained is also applicable to rotating machinery. Compared with rotating machinery and linear cascade, the geometry of a single blade is simple, make it easy to carry out a series of fine measurements and numerical simulation. It should be noted that the tip-leakage vortex cavitating flow may be influenced by a lot of factors such as incoming flow, incoming velocity, attack angle, and reference pressure, and surface roughness, and gap size. Thanks to the research in the past decades, the influence of these factors has been understood well. While how the gap size influences the tip leakage flow and the reasons behind it are still not clear. Therefore, our study is mainly focused on the influence of gap size on the tip leakage flow. The second part is some description of experimental and numerical setup. In our investigation, the NACA 0009 hydrofoil with a rectangular platform is employed to generate the tip leakage flow. The reason that we choose this foil is that there have been a lot of experimental measurements for tip leakage flow. For example, Dr. Fahad from EPFL conducted a series of measurements with PRV and high-speed video. This picture shows the measured evolution of the vortex circulation with different gap size. And this video was provided by Dr. Fahad. This is the tip leakage vortex. Here we abbreviate as TLV. This is the TLV cavitation. This is the tip separation vortex. Here abbreviated as TSV. This is the TSV cavitation. This is the sheet cavitation. A series of measurements in the cavitation tunnel of EPFL is conducted. This data could be a valuable reference for our numerical simulation. This is the computation domain in our current simulation. This is the direction of incoming flow. The speed is set as that in the experiment. The chord length is 100 millimeters. The attack angle is set as 10 degrees. In our simulation, the scalar source cavitation model combined with the LES is utilized for the simulation of TLV cavitation. It should be noted here, the normalized tip clearance tau was used. This value is defined as gap size over maximum flow thickness. This is the mesh that we generate for our simulation. Here we use the Cartesian cut-cell method. This method has many advantages, especially its easy self-adaptation. As shown in this picture, the mesh in the region with TLV is refined specially. This slide shows the comparison between the experimental and numerical results. The corresponding gap size is 10 millimeters in physical distance. The left is the video for the instant. The right is the time average one. As we can see, a quite good agreement can be obtained. The development of TLV cavitation is captured quite well. However, if we increase the gap size, the strength of TLV cavitation will be significantly underestimated. Just as shown in this slide, if the gap size increases 20 millimeters, the predicted TLV cavity is much weaker. if compared with the high-speed video, it seems a little strange for us. We didn't change any numerical setup, but just increase the gap size. The method didn't work anymore. That is the motivation for the following work, and we should find the reasons. Then we go to the third part of my presentation. We proposed a new cavitation model. It should be noted here, the tip-leakage vortex flow is very complicated, and many factors may influence the prediction of TLV cavitation. So firstly, to simplify the problem, we change the flow from the rectangular platform to an elliptical hydrophore, such as this case. The main vortex structures around the elliptical hydrophore are only the separation vortex from the leading vortex and the tip vortex. So the tip vortex generated by the elliptical hydrophore is much simpler. Moreover, in this case, the flow tip is set at the middle of the cavitation tunnel. So the influence of wall can be ignorable. This case is very simple and is helpful for us to think about the simulation of vortex cavitation. Another advantage of this case is that it is very friendly for the mesh generation. Firstly, we can generate a coarse mesh and then specially refine the cells around the tip vortex for several times. A quite good mesh with high quality can be obtained. In our simulation, the cell numbers for the basic mesh is only about 1.3 million. After 4 times refinement, the cell numbers increase to near 12 million. Most of the increased cells is around the tip, which is good for the simulation of tip vortex cavitation with limited computing results. We compared the predicted tangential velocity distribution around the tip vortex by 4-case mesh with the measured date. It indicated that with the refinement of mesh, the numerical result get closer and closer to the experimental date. And for the mesh case of M3 or M4, the difference between the predicted and the measured tangential velocity distribution is almost negligible. Therefore, we choose the M3 as the final mesh. A quite good prediction for the tangential velocity distribution is obtained with M3. However, when we check the predicted tip vortex cavity, the result is not so satisfying. For example, for the 2 case with cavitation number, for example, the cavitation number equal 2 or 1.5 case, the tip vortex cavities are both significantly underestimated. Just like the problem we face in the simulation of TLV cavitation. We try to find the reasons and analysis many possible factors, such as the predicted time average pressure and the pressure fluctuations. But it seems there's no problem for the prediction of the pressure field. Finally, the nuclear around the tip vortex attracts our attention. Many researchers, example, one recent POF paper by Chen from Zhejiang University has indicated that the tiny bubbles with non-condensable gas may roll up around a tip vortex and get trapped in its core due to the pressure gradient of force, as shown in this picture. Such bubbles migration leads to an increase of gas concentration near the vortex core, which may significantly modify the local cavitation process. To capture the change of gas concentration near the vortex core by nuclear migration, we conduct a simulation with the so-called discrete phase model. We released many tiny gas bubbles upstream, and then the movement of these tiny bubbles will be described by the this DPM equation. This slide shows our numerical results. It is very clearly that the concentration of gas bubbles around the tip vortex has a significantly increasement. According to our numerical results, the concentration of nuclear at the tip vortex center may be increased up to 100 times of the initial concentration. Such a great concentration of nuclear obviously will influence of local cavitation process. However, when we look at the deviation of our now popularly used cavitation models, such as Skerner source cavitation model or the ZGB cavitation model, these two models are both based on the simplified of RP equation. We can find that in the simplified RP equation, the partial pressure of non-condensable gas is emitted directly, which means these models cannot reflect the influence of non-condensable gas. Someone may argue that there are some model parameters such as here, alpha NUC in ZGB model that represents the cavitation nuclear. However, it should be noted here, such kind of parameters are unified for the whole flow field, which is far away from the real case. So it is necessary to find a more reasonable way to reconsider the influence of cavitation nucleus in the simulation of tip vortex cavitation. If the reason for the underestimation of tip vortex cavitation is the emission of gas partial pressure in the original model, the solution here is clear. That is to include the gas partial pressure in it. Here, the pressure in the bubble includes two parts, PV and PG. The PG is the new we added. This slide shows how we consider the influence of gas partial pressure in cavitation model. It includes the migration of gas bubbles and their merging with vapor. During this process, the perfect gas law in adiabatic state is utilized to describe the growth or collapse of gas bubbles. And the total pressure after the emergence is recalculated according to the law of partial pressure. This is the chart of the calculation process with this model. Here, the Euler method is used to solve the global flow field, and the Lagrange method is used to track the migration of non-condensable gas bubbles into the vortex core. Based on the simplified RP equation, the connection between the local gas concentration and its effect on cavitation is modeled, and the mass source term in the original cavitation model are modified. Finally, we proposed a new Euler and Lagrange cavitation model. For more detail, you can refer to our recent IJMF papers. Obviously, any attempt any attempt to model cavitation for taking into account the non-condensable gas requires the knowledge of the initial gas content. According to the independent measurements, the mass concentration of nuclei is in this range. In the current study, we assume an initial mass concentration of non-condensable gas with this value. Here, we mark it as CG0. This slide shows the influence of 3 different initial gas concentration on TVC prediction in the exception case. For example, in present case, the cavitation number is equal to. It can be observed that the tip vortex cavitation is still underestimated with 0.4 CG0. With a high initial gas concentration, the predicted cavities become stronger and stronger. When CG is over 1.6 times, the predicted tip vortex cavity is a little overestimated. The best prediction for the tip vortex cavity is provided with 1 times CG0. Therefore, this value is recommended in our current case. With this initial gas concentration, we simulate the case for cavitation number equal 1.5 case. As shown in this picture, a quite good agreement is obtained between the predicted tip vortex cavitation and the experimental picture. With this new model, we recalculate the TLV cavitation with large gap size, which is significantly underestimated by the original model. This is original model prediction. This is the new cavitation model prediction. As shown in this slide, left is the video for the instant, the right is the time average one. A significantly improvement in the prediction can be obtained when compared with the original model. So this model has good performance for the prediction of tip vortex cavitation and the TLV cavitation, especially for large gap size. Based on the above numerical method, we then discuss the characteristic of TLV cavitation. This movie shows the typical evolution of TLV cavitation and a vortex structure in a tip-leakage flow. 3 distinct vortex structures in the tip-leakage cavitating flow can be clearly observed, including TLV cavitation. This is a tip-leakage vortex cavitation, and TSV means tip separation vortex and induced vortex. TSV is formed due to the flow separation on the foretip at the pressure side and moves towards the suction side to the moves towards the suction side due to the tip leakage flow and roll up of TLV. Therefore, TSV has the same rotational direction as TLV. Induced vortexes are formed from the end wall. Here, this place is the end wall. Induced vortex are from the end wall by TLV, and its rotating direction. Its rotating direction is opposite to that of TLV, which will accelerate the dissipation of TLV. These 3 movies shows the development of TLV cavitation and the corresponding vortex structure with 3 typical gap size. We can find that TLV cavitation and the corresponding vortex structure can be significantly modified by only change the gap size. For small clearance, as shown in this slide, due to the great pressure difference between the pressure side and this is the suction side, the velocity of the leakage flow is rather high. Moreover, the gap is quite narrow, so there is no enough space for TSV to roll up by itself. Therefore, TSV merge with TLV almost from the leading edge. Further downstream, the extremely proximity of TLV to the end wall leads to complex induced vortex, which has a strong dissipation effect on TLV. And the TLV can just sustain till half the code. For middle clearance, the TLV and the TSV both coming to being from the leading edge, separated by the foretip. There is a relative short period during which TLV and TSV develop independently. Then TSV is loaded into TLV due to the influence of tip leakage flow and the entrapment of TLV. The corresponding cavitation patterns also present such a process. Afterwards, the mixed vortex develops downstream and release the complicated induced vortex. The interaction between the TLV and the induced vortex is believed to be responsible for the wandering of TLV cavity. For large clearance, TLV and TSV are both weak. The independent development starts longer till the trailing edge. Correspondingly, TSV cavitation is so weak that it is hardly to see. And then the TLV cavity is rather slender. The low strength of the mixed vortex and its distance from the end wall lead to low intensity of induced vortex, which even cannot be displayed by the isosurface of the Q criteria. Therefore, the TLV cavity for large clearance is more stable if compared with that case with a small or middle clearance. The previous discussion showed that the interaction between the TLV and the TSV and the induced vortex significantly influenced the development of the TLV cavity. At the same time, the evolution of TLV cavitation will also influence the distribution of local vorticity. This picture shows the actual vorticity distribution at the typical moment for middle gap size. As is shown in the 11 cut planes, the actual vorticity inside the cavity decreases as the TLV cavity develops downstream. To see it clearly, 3 typical cut planes as shown in this picture, we choose this 3 cut plane. Here, the actual vorticity counters distribution was shown on these 3 cut planes. And the black line represents the location of TLV cavitation. At the section with X over C equal -0.2, the actual vorticity inside the cavity is relatively high. However, at the section with X over C equal 0.4 and 1.2, the actual vorticity inside the cavity is becomes slower. The reason for this phenomenon is not yet clear. To answer this question, the vorticity transport equation is employed in our following discussion. As is shown in this equation, the term on the left-hand side represents the rate of the vorticity change. On the right-hand side, the first three terms are the staging term. This is the staging term. This is the vortex dilation term, and this is the barochronic torque term. It should be noted here, the viscous diffusion is much smaller if compared with the other three terms, so it will be omitted in the following discussion. This slide shows the distribution of staging term on these three cut planes. Although generally speaking, this term is dominant during the evolution of the whole evolution of cavitation. In our current case, it mainly concentrates outside the TLV cavity, and no obvious distribution inside the TLV cavity. It indicates that this term may modify the vorticity distribution outside the TLV cavity, but leaves little influence on the vorticity inside the cavity. The distribution of the dilation term, as shown in this slide, indicates that this term is very important and with the same magnitude as the staging term during the whole tip-leakage cavitating flow. It should be noted here that the dilatation term is negative inside the TLV cavity, which suggests that the local vorticity is decreasing. However, the dilation term around the TLV cavity is positive. Thus, the effect of the dilation term is to transport vorticity from the TLV cavity inside to the outside, which is the reason for the decrease of the vorticity inside the TLV cavity. The barochronic torque term is much smaller if compared with the staging or the dilation terms in the tip-leakage cavitating flow, and is mainly concentrated near the liquid and vapor interface. Thus, the pressure and density gradients are not badly misaligned in the current case. Another issue that has attracted much attention in studies of cavitation is the cavitation and turbulence interaction. However, due to the complexity of tip-leakage cavitating flow, there have been fewer reports on the interaction between the cavitation and turbulence in tip-leakage cavitating flow. According to the measurements from Johns Hopkins University, turbulence kinetic energy, here we abbreviate as TKE, inside the TLV core is higher, while with a little production, but the reason behind it is still unknown. And in our case, as shown in this slide, a higher distribution of TKE can be also seen inside the TLV if compared with the outside nearby, which is similar to the measured result from Johns Hopkins University. To find out the reason behind it, the TKE transfer equation was used. The left-hand side of this equation denotes the rate of change of the TKE. The three terms on the right side represents represent the production, this is the diffusion, and this is the dissipation terms. This slide shows the distribution of the production term we can find a lot of TKE production around the TLV cavity, but not inside the cavity, which indicates that the TKE inside the TLV cavity is not produced locally. This slide shows the distribution of the diffusion term of TKE inside. I mean the diffusion term of TKE inside the cavity is positive. This is also positive, and high pressure. While at the outside is negative. It is negative. This kind of distribution suggests that the high TKE inside the TLV cavity is transported from the nearby region to its inside. This slide shows the distribution of the dissipation term. Compared with the two terms we mentioned before, this term is much weaker. In the last section, we discussed the characteristic of TLV cavitation. For the engineering, there are urgent engineering requirements for how to control or suspect the TLV cavitation. For the past decade, several flow control strategies have been proposed to mitigate TLV cavitation in hydraulic machines. These strategies can be divided into two categories: active control strategies such as water or gas injection, boundary layer suction, or and their combination, and the passive control strategies, including tip or cast treatment, and the vortex generator, and the winglet or tip extension. Anyway, this method is not always so satisfying in practice. Among these methods, two kinds of control methods attract our attention. One is the so-called the anti-cavitation leap, which is a metallic piece attached to the tip of the blade on a, here this is a coupling turbine. It is reported that this device may increase the radius of TLV and further suppress the TLV cavitation. This device can work well in large gap size. However, if the gap size decrease is very small, this method is ineffective. Another control method is the grooves on the end wall. Dr. Fahad suggests that these grooves can significantly suppress the TLV cavitation. However, the effect of grooves seems very sensitive to the gap size. When the gap size increased 2 millimeters, no remarkable suppression effect was observed. In short, the grooves can work well in small gap size. It should be noted here, even though the effect of the conventional grooves or the anti-cavitation leaps, here we abbreviate as ACL, are both strongly dependent on the gap size. The effect tendencies of these two methods are opposite. The CGs can significantly suppress the TLV cavitation with small gap size, while the anti-cavitation leaps is more effective at the relative largest gaps. Therefore, if we can find a device that can combine these two main advantages, then maybe we can obtain effective control strategies for all gap size. Based on this idea, the so-called overhanging grooves, here we abbreviate as OHGs, is proposed as shown in these pictures. Similar to the conventional CGs, the OHGs are obtained by attaching several taps. The several taps connect with each other by a slender beam. The difference between the CGs and OHGs is that OHGs extend beyond the suction surface. Here, it extends beyond the suction surface, which is similar to the anti-cavitation lip. The sculpture of OHGs and several key parameters is shown in this slide. This slide combines the observation of TLV cavitation of the OHG this is the baseline and the ACL, and the CGs and the OHGs with different gap size. The experimental results indicate that the ACL can weaken the strength of TLV cavitation at the middle and large gap size, but no remarkable difference is observed between the baseline and the ACL case when the gap size is small. While for the case with CGs and OHGs, both of them show a better performance on TLV cavitation suppression at a small gap size if compared with that of ACL case. With the increase of the gap size, the suppression effect of the CGs is not as good as that the OHGs. It should be noted that unlike the grooves at the end wall, the CGs in the present investigation is attached at the fault tip, which suggests that the leakage flow may be disturbed by CGs even with the increased gap size. In a word, anyway, our OHGs shows a satisfying suppression effect on TLV cavitation within the entire range of gap size. Moreover, due to the simple structure, the OHGs are also easy to implement in hydraulic machineries with very low cost. The geometry parameters are critical to the effect of OHGs. Therefore, a primarily optimization design is also conducted. This is the final optimal parameters for OHGs according to our experiments. This slide shows the comparison between the observed TLV cavitation of the OHGs with the optimized parameters and the original form. A quite satisfying suppression on TLV cavitation can be obtained for all three case gap size. A deep investigation about the mechanism for the suppression effect of OHGs on TLV cavitation is also conducted. In short, for small case, for example, in the first line, the strength of TLV will be weakened due to the increase of the flow resistance in the gap by OHGs. For middle and a large gap size case, for example, this is the second line and the last line. The radius of TLV is increased due to the existence of the part beyond the suction side of all the OHGs. That's the proposed the OHGs provide a good satisfying suppression on TLV cavitation over a wide range of gap size. And recently, our group is trying to check its effect in actual hydraulic machineries, and I will share you once we have new results. And finally, come to the summary and the conclusions. And this is the summary for the report today. We proposed a new cavitation model, and we discussed the characteristic of TLV cavitation and we proposed a new TLV cavitation suppression device. For more detailed information about the work, you may refer to the following 3 papers. And finally, I want to express my sincere gratitude to my colleagues, Dr. Chen and Dr. Long from Wuhan University, and Dr. Peng from China Ship Scientific Research Center, and Dr. Fahad from EPFL in Switzerland. Also, I would like to appreciate the financial support by China Scholarship Council, and Mr. Chen visited EPFL in Lausanne for 1 year as a joint PhD student, and we have a good collaboration with Dr. Fahad. That's all my presentation. Thank you very much for your kind attention. Thank you.
Thank you, Professor Ji, for your brilliant talk. We really learned a lot from your beautiful talk. Okay, now the floor is open for questions. So you can raise your hand or you can type your questions in the chat. Okay. So
hello,
then,
Professor Sun.
Yes. Okay, good.
This is Chen Wu from okay, thank you, Professor Sun. This is Chen Wu from Beijing Institute of Technology. Thank you for organizing such a wonderful presentation for us, and also thank you very much for Professor Ji's such a wonderful presentation. I think the Professor Ji's topic is very interesting, and I have several questions I want to discuss with Professor Ji. So first question is, how do you consider the non-condensable gas in the numerical simulations, such as how to decide the initial gas concentration like CG0?
Hey. Okay, I will share the slides. Yes, thank you very much for your question. In our simulation, the non-condensable gas bubbles will be released the upstream, and then their migration will be calculated by the describer like this. Okay, I show the slides. Like this, their migration will be calculated by the described phase model, the DPM model, in which the drag force, gravity, and the pressure gradient force are considered. As for the initial gas concentration CG0, the value should be decided according to the water quality in the cavitation tunnel. In our case, we don't have the equipment for the measurement of nuclear. So, but we found some reference. According to the one POF paper by Zhejiang University, they suggest the mass concentration of nuclear. So we, according to Chen's work. Thank you very much for your question.
Thank you, Professor Ji. And I also have another question is, as you mentioned, both the vorticity transfer equation and the turbulent kinetic equation, turbulent kinetic energy equation have been adopted in your research. I wonder, is there any relations between them? For example, is the stretching term in the vorticity transfer equation corresponding to the production term in the kinetic energy equations?
Okay, thank you very much for your question. This question is very interesting. To be honest, we didn't consider the connection between the vorticity transfer equation and the turbulence kinetic energy. equation before. So according to my knowledge, the stretching term is maybe is possible to enhance the local turbulence. So it may be possible there are some relationship between the distribution of the stretching term and the production term. We maybe later we will check this problem in our case. Once we have some findings, I will share with you. Thank you.
Thank you, Professor Ji.
Okay, so we have another question from the Professor Yu Sheng Zheng. You can unmute yourself.
Okay. Hello, Professor. Thanks for your great. Thanks for your great presentation. I have two questions. The first question is about the physical difference between an experiment and a numerical simulation. In experiment, it is strong fluid and structure interaction between the hydrofoil and the cavitating flow. The tip-leakage vortex or leading edge cavitation may lead to deflections or vibrations, which will feed back to the flow field, while in numerical simulation, the only fixed wall conditions are considered. So the question is, why the influence of the fluid and structure interaction can be ignored in your simulation case?
Okay. Okay. Thank you very much for your questions. Okay, maybe. Thank you very much for your question. You know, cavitation is a very complicated flow phenomenon involving many complex flow phenomenon. Just as you point out, actually the fluid and structure interaction between the flow and the cavitating flow may be very strong in experiment. So if possible, it may be necessary to consider the influence of FSI in the simulation of cavitation. However, you know, in our case, it is difficult to consider. It's difficult to consider TLV. We simulate the TLV cavitation and consider the FSI effect. So maybe in a later we will consider this. So thank you very much.
Okay. Thank you for your answer. Professor, I have another question. The question is about the application of the control method for tip-leakage vortex, because the investigation is carried out on a hydrofoil, which is a non-rotating structure. For the pumps, the turbulence, the blade is rotating, and the velocity of the tip can reach as high as 40 meters per second, which is much higher than that in the hydrofoil case. So the second question is, what will be the difference by taking the rotating effect into consideration?
Okay, thank you. Thank you very much for your question. I will show your slides. Okay, this slides. Yeah, for the rotating effect on the control method, I agree with you. The rotating effect will be very strong in pumps or the turbines. And for our present case, we didn't consider in the rotating machinery, but one of my students is conducting the numerical simulation for the OHGs, as this OHG is in a pump. I will share you if I have some findings. Thank you.
Okay. Thank you for your answer. I have no other questions. Thank you.
Thank you.
Okay. So I think Dr. Liu or Professor Liu has a question. Okay, you can unmute yourself.
Okay. Thank you. Excuse me. Is it?
Yes, you can.
Yes.
Thank you very much for your nice talk, Professor Ji. I'm Yun Qiaoliu from Shanghai Jiao Tong University. I'm not so clear. How do you connect gas concentration with the gas pressure? Do the bubble grow when they enter the vortex core, or do they merge?
Okay. Thank you very much for your question. It is a little complicated. I need to show the. Maybe here. Yeah, maybe. Okay, I should. Yeah. Thank you very much for your question. It is a little complicated. To be simple, a higher partial pressure of non-condensable gas can be provided if there are more gas. If there are more gas nucleus, which means the total pressure of the bubbles can be higher and higher, and then a higher local pressure is needed if one wants to suppress the growth of these bubbles. Or in another word, cavitation is easy to happen. To build the connection between the gas concentration and its partial pressure. The law, the perfect, the gas law in adiabatic state is utilized, and the total bubble pressure after the emergence is calculated according to the law of partial pressure. Maybe for more detail, you can refer to our recent IGM paper. Thank you very much.
Okay, thank you. I'm clear. Thank you very much.
Okay,
thank you.
So we have a question from Xiaoyang Zhao. You can mute yourself. Unmute yourself. Okay.
Hello, Professor Ji.
Yeah, thank you.
I'm Zhao Xiaoyang from Beijing Institute of Technology, and I am very deeply impressed by your great work. Thank you for your presentation, and I have two quick questions. This first one is, how did you refine the mesh around the hydrofoil and the tip-leakage vortex region? Can you tell us some knowledge or experience?
Okay, thank you. Here we use the Cavitation capsule. We use the. Thank you very much for your question. Here we use the Cavitation capsule method. This method is very easy for the very easy mesh for its self-adaptation. The self-adaptation, we can easy to refine the area we care. So here we refine according to some variables. I cannot remember exactly, we refine it. It's very careful, and finally we can capture the vortex cavitation in detail. So that's my answer. Thank you very much.
Okay, there is another question. The overhanging grooves have shown significant influence on the TLV cavitation, and the angle of grooves is 45 degrees in your research. Is it the best angle?
Okay.
So Professor Ji, Could you give a quick answer? We have to close the presentation soon. Okay.
Oh, okay. Okay, I need to show the. Here. Yeah. Thank you very much for your question. And for the choice of this angle, we reference the work by one PhD student from EPFL. They carry out a detailed experimental measurements, and they found this group with 45 degrees is the best angle. So here we just refer to the EPFL's result. We didn't do the research about this one. Thank you.
Okay, thank you.
Okay, so thank you. So we have many questions. I suggest if you have more questions, I suggest you direct contact Professor G for discussions. So Professor G, thank you very much again for your brilliant talk. So okay, we welcome Professor Balachandra to give us final remarks.
Okay. Thank you, Professor G. This was a fascinating talk. And also, I want to thank Professor Chao Sun for both of you to bring together a large audience. And I also want to thank the audience because I was really captured by the many questions that the audience had. I had some questions, but I didn't have a time to ask because there were some brilliant questions from the audience. And I'm really I'm very delighted to see that the Spotlight Seminar was able to provide such a venue. And I want to remind the audience that we have another excellent seminar in 3 weeks, which is the first Tuesday of December. That will be the last talk. And I would like to see as big an attendance as possible from all around the world. And I want to say thank you and have a great day, the rest of the day. Okay.
Thank you. Thank you.
Thank you. Bye.
Yeah, bye. Thank you.